In this video, we're going to talk about two main things, and that's line symmetry and rotational symmetry. So line symmetry is when a figure can be mapped onto itself by a reflection in a line. And a figure can have more than one line of symmetry. So if you look at the butterfly over here on the right, that the line of symmetry is at line M. So one thing you're going to be asked is how many lines of symmetry does the figure have? So in this first one, you just have to draw them. So we'd have one right there, two, and that would be it. So because if we did draw a line like this, if you notice, this point wouldn't be mapped onto the other one on the other side. It does not match up like that. So then on the next figure, we could go up and down and go through each of the middle of the sides. So that's 1, 2, 3. And then you could also go through the corners. So 4, 5, 6. So there'll be 6 lines of symmetry in that figure in the regular hexagon. For the ram, if you notice, the only line of symmetry we could have would just be one right down the center. For the flower, you have to be careful, so we could have a couple of them. If you go between the petals, so it'd be 1, 2, but then we could draw 3, 4, because the petals themselves could match up on top of each other, so there would be 4 lines of symmetry in that figure. Rotational symmetry is when a figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. So the center of symmetry is just that point that it's rotated about. So just like rotations before, they can be rotated clockwise or counterclockwise. So when you're actually looking at one of the figures, what you want to do to figure out if it has rotational symmetry and the degrees that it has is you want to look at each of the points and see almost if I rotate this figure around, that if I went there, that the points are not going to line up with each other. So the only thing I can do is if I go all the way around and all the way around again, that there's 2 rotations in there, so 2 times that would be in the same location. So if I take 360 and divide that by 2, each of the degrees would be 180 degrees. So yes, it does have rotational symmetry, and it would be 180 degrees. For the next figure, there would not be any rotational symmetry because there's no points along the way. I couldn't rotate it onto itself here because then it would be pointing up, not down. So there's no other way for me to get around on that one. For the hexagon, notice that it's a regular hexagon, so all the angles are going to be exactly the same. All the angles are the same. So 1, 2, 3, 4, 5, 6. I could move it 6 times around. So if I take 360 divided by 6, I get 60 degrees. So yes, it is rotational symmetry, and the degrees are 60 degrees. For my octagon, then, I have 4 equal points. So notice they're the same distance all the way around, so I have 4 spaces all the way around that I could rotate it at any of those locations. So I take 360 divided by 4, and I get 90 degrees. So I would have 90-degree rotation, and yes, there is rotational symmetry. Then for the very last one, for my flower petals, that if I kind of start in the middle, that one petal would rotate to the next petal, to the next one, to the next one, to the next one, and again I would have 4. So this would be yes again, and it would be 90 degrees just like I got on the octagon. For this question, we need to identify the line symmetry and rotational symmetry of the equilateral triangle at the right. So if you remember, an equilateral triangle means that all 3 sides are the same, but it also means that all 3 angles will be the same. So for the line symmetry, I'm going to do this in purple. So I have 1 right down the center, 1 down the center of the next corner, 1 down the center there. So I actually have 3 lines of symmetry. But then for rotational symmetry, we have to go around 3 times. So we take 360 divided by 3, and I get 120 degrees. So 120 degrees is my rotational symmetry, but then my line symmetry, I have 3 lines of symmetry. So I've got the 3 lines there, but then the only one that has the 120 is that very last one. So my final answer would be D as in dog. For these last 3, how many lines of symmetry do the figures have, and does it have rotational symmetry, and if it does, what's the degree? So we're asked 2 parts. So first with the line symmetry, if I drew a line down the center, these little bubbles, since they're not the same on both sides, they would not overlap each other. So this has no line symmetry. But for rotational symmetry, each of them are the same space away, and if I rotate it, it would be the same all the way around. So that 6 times, so 360 divided by 6 gives me 60 again. So for my rotational symmetry, I have 60 degrees. All right, for the next one, for my line symmetry, if I put a line right along here, this arrow would have to end up here, and that does not make it the same. If it went up and down, the same thing would happen. It would flip over, and it would not be the same. So again, there's no line symmetry here. For my rotational symmetry, if I rotate this around, it would only end up at one spot and then back on itself. So there's 2 times I could rotate it around. So 360 divided by 2 gives me 180 degrees. So for my rotational symmetry, I get 180 degrees. For the next one, for my line symmetry, there's quite a few spaces I could do this. So I can do it right on these points. So 1, 2, 3. But then I also have the kind of snowflake corner parts of it. So that's 3, 4, 5, 6. So with my line symmetry, I would have 6 lines. Then for my rotational symmetry, I would have to start at each corner. So I'd have 1, 2, 3, 4, 5, 6 again. So 6 times around. So my 360 divided by 6 gives me 60 degrees. So my rotational symmetry gives me 60 degrees that I would have for the symmetry.